Okay, let's continue. The next topic is rotation. So when a tree is already in balance, instead of focusing on how to color the tree, we should rotate the tree to make it balance. Okay, so and you should see rotation in some other courses. And if you are the first, if you see the rotation first time here, it could be a little bit hard. But let me explain it to you. So if we have a y as the root of the subtree, and then we have the x as the left child, and then we have three subtrees. So for those three subtrees, A, B, and C, I don't worry about the size of those trees. I just call them subtree A, B, and C. Okay, so if we want to do a right rotation, and what we are going to do is for the x here, we are going to make x the root of the subtree. And then for the y, it will be the x right child. And then for the b, the subtree b, it used to be the right subtree of x. Now it will be the left subtree of y. So this is a right rotate. And if you want to do a left rotate, and then you just take the image on the right side and then rotate it back to the left side. Okay, so this is the very high level description of a rotation. And you may ask, why can we do that? We are dealing with a binary search tree or a Redblack tree, right? So when we are doing this rotation, are we going to break any of the property? So let's consider the binary tree property. So for a binary tree, this means y is greater than x. Okay, and then a is smaller than x and b is greater than x, but both a and b are smaller than y. And for the c is greater than y. Okay, so if we do the rotation, so a is smaller than x, so same thing here, a is smaller than x, so that's okay. And for the c is greater than y. And on the original tree, c is greater than y. So that's also good. And the tricky part is b. So for the b here, b is greater than x, but b is smaller than y. Let me say that again. b is greater than x because b is the right child of x. But since b is on the left subtree of y, and then b is smaller than y. And how about here? b is smaller than y and b is greater than x. So we haven't broke anything yet. Okay, so far we are good. So that is the the right rotation and the left rotation. So, and then if we want to consider how to code it, how this can be done. So the implementation should be x keeps its left child, which is a, and then y keeps the right child, which is c. And then x right child becomes y's left child, and we are referring to b. And the last one, x and y's parent exchange. So this means, well, let me write here. So there could be a parent node of y. So if there is a parent node of y there, and now this will be x new parent. Okay, so we are only rotating a subtree, and then for the parent, it's not changed at all. So the next part, what is the running time? So this is a primitive step. This is a primitive step, and x right child becomes y's left child. So we are doing a assignment, so that is also a primitive step. And eventually we want to change the parent of the y's parent to x parent, so that is a primitive step. So if you add everything together, that is a O1, which is a constant time. Okay, so now it is the interesting part. We want to do a left rotation of 9. Okay, so 9 is here. So if we are doing the rotation on the 9, and this 9 is the root of a subtree, right? So when we are doing a left rotation, and then 12 will be the new parent. So the first thing, let me remind you, we are rotating a subtree. But for the other part of the tree, for example, 9's parent, 7, we are not changing anything, right? So if you see here, and this is the parent of y. And after rotating the subtree, now this parent will be, again, stay here. But its child will be changed to x. That's the only thing got changed. Okay? So this means we are only touching this part. We are only touching the subtree with the 9 as a root. And for 7 and 5, we are not changing them at all. So, and then we are doing a left rotation, right? So I'm going to divide this subtree into 3 parts. So here, this part, I call that, what is that? Can I erase it? No, well, never mind. Okay, yep. So let me do this again. Okay, the first part is this one. I call that box 1. And this part, the right subtree of 12, I call that box 2. And 12's left child, which is 11, and the subtree here, I call that box 3. Okay, so I'm only touching 9 and 12 because I'm doing a left rotation. However, I'm not paying any attention to 8, 11, or the box 2. I'm just calling them box 1, box 2, and box 3. So now we are going to start from a subtree like this. So we have 9 here, and we have a 12 here, and 9 we have box 1, and then we have box, what's that? Box 3 and box 2. Okay, so this is the tree we are going to rotate. So how do we rotate that? So that is, we have 12 here, and then we have 9 here. And after that, 9's left child should stay here, and 12's right child should stay here. And for the box 3, now it is 9's right child. Okay, that's done. That is exactly the rotation we learned here, right? So I'm not worrying about any other nodes. I'm only paying attention to the node 9 and 12. And after the rotation, now I can replace the box 1, box 2, and box 3 with the corresponding subtrees. So I got this version. Okay, so it's nothing fancy or tricky. We are trying to just rotate a tree, and we only pay attention to 2 nodes. They are 9 and 12. So that's it. So the next part, let's come back to the insertion. So for the insertion algorithm of a red-black tree, the rule is when we insert a new node X into the tree, we always start with a red node. So the new node will be colored as red. Well, will this violate some of the properties? Yes. And the only red-black tree property might be broken will be the property 3. And property 3 says we can't have any 2 consecutive red nodes. And this may break that property. And after that, we have to fix it. So, and if we have to fix it, and the time will be a O log n. So this is the code. It sounds scary, right? And that's even more code. That sounds even more scary. Okay, and we ain't gonna really go through the implementation, but let me show you the idea. So the case 1. So the case 1 is if we insert a new node X. So the X is here, right? So if we have the new node X, X parent is a red. So X parent A is red, and X ankle is also red. Okay, so we have the problem of consecutive two red nodes here, A and B, and the B is newly inserted, and we call that X, right? So now we need to fix the tree. And before we do that, let's pay attention to the little triangles. So for those little triangles, well, I don't know what they are. If we just inserted X, probably they are all null pointers. But we don't have to worry about that, as long as we know for all the little triangles they have the same black height, and then I'm good. Okay, so how do we fix that in this case? If we can't have two consecutive red colors, one of the easiest way is, okay, for the X you stay as red, and for X parent A and X ankle D you both change to black, and for X grandparent, which is C, we change it to red. Okay, so think about that. Before we insert X from C to any of the leaf, so it should be C as one black node, and then all the little triangles they have the same black height. And when we insert the B, we are breaking the rule number 3. Then if we want to fix that, we are coloring the X and the grandparent to be red. And then for the parent and ankle, they are both black. So it's guaranteed the black height will stay the same. So if you go here from C to A and then to this node, you count 2 black heights. Or if you are considering the black height of each triangle to be n, and then from C to each of the leaf, it will be black height plus 1. So n plus 1 will be the black height of C, guaranteed. So are we finished? So if C is the root of the entire red-black tree, and the answer is yes, we finish. However, well, this may just be a subtree, right? So how about we have even more nodes up? If we have a black node here, so probably in this case, after recoloring this tree, nothing is broken, right? So this is black, and then C is black, so A and B cause the trouble. And after recoloring this tree, and then A and B, A is black, B is black, and C and B are red. So if you count the black height of this node, so this, if we count the black height of this node, that is 1, 2, and then we have n here. So let's just assume for each of the triangle they have the black height of n. So this case, well, for this node it will be 2 plus n as the black height. So if we do this one, that is 1, and we skip this one, and that is a 2, and then we have an n here. So no matter which way we go, it will be the 2 plus n as the black height of the node X. So it doesn't, after we recolor the tree, now we are good to go. So let me remove all the markers. And no, I want to remove all the markers. Okay. So now if I remove all the markers, and let's assume we have a red X here. If we have a red X here, now the story will be changed. Okay? So if we have a red X, and after we recolor the subtree starting with C, now X and C, they are two consecutive red color again. That is the reason we say now the C will be the new X. So we have to fix the tree again. But for all the nodes lower than C, probably we are fine. But we have to fix the tree all the way up. Probably we have to fix the tree all the way up to the root to make the red-black tree valid again. Okay, I'm going to stop here, and I will see you in the next video.